Okay, video is on. So, I want to continue a little bit about Lie algebras and weight systems, so functionals on A. And then, if we're lucky, compute the weight system of GLN. That will probably go into next time. And I'm kind of looking forward to it because, you know, I assigned one homework assignment in which the only content was signs. And for GLN, the only content is Kronecker delta functions. So everything, absolutely everything, is delta ij. Okay? But still, you can assemble Kronecker delta functions to make interesting things. So that's, I hope we'll get there. But before that, so last time we've proven that A is isomorphic to A trivalent, and I'm not going to repeat the definitions, but we actually didn't quite finish the proof and I simply forgot about it. So we've proven that A is isomorphic to to the space that you get by looking at trivalent diagrams modulo the STU relation. We never mentioned as antisymmetry, we never mentioned IHX, we didn't prove them, we didn't use them. So the reason is that in fact they are consequences of the STU relation. So really the STU relation implies this one and implies that one. And the only reason I tend to put them is because it's for convenience. It's convenient to think that they're a part of the definition. Okay? So I still have to show you that the STU relation implies antisymmetry and implies IHX, and both proofs are silly. Both proofs are very, very easy. Okay? So suppose you want to prove IHX. So you have a big diagram, right? And somewhere inside it, there is an IHX combination. Or more precisely, you have three big diagrams, and somewhere, and they're all identical, except one of them has an I somewhere, and in the same place, the second has an H, and the third one has an X. So first of all, using STU relations and using connectivity, we can, so suppose there were, so suppose this IHX was far away from the skeleton, we can always, using STU relation, get rid of all the vertices on the way there, and then it's adjacent to the skeleton. So I really only need to prove the IHX relation in the case where one of the vertices, and I may as well pick it to be the lower left vertex, is actually on the skeleton. So here is the picture. Here is I lying on the skeleton, here is H lying on the skeleton, here is X lying on the skeleton. And then it's completely brainless. You just use STU to get rid of this vertex, you get these two diagrams. You get you use STU to get rid of this vertex here, you get these two diagrams. For the last one, you get these two diagrams. You still have an extra vertex inside. So you use STU again to get rid of it. So these two diagrams become these four. These two become these four. And these two become these four. And then you look at it, and they all cancel. So it's really not interesting. So I don't know, this one kills this one, you know, I'm not going to go through it, it's not interesting. The only interesting thing to say is that we've actually said that already. Okay? So at some point I checked that the bracket defined as the bracket of A and B is equal to AB minus BA. I checked that it satisfies the Jacobi identity. Okay? And if you look at this very carefully, this is exactly what is being verified here. Namely, if you write A, B, and C on the three ends that are not on the skeleton. So, but you do it consistently for all diagrams. So, I mean, this one is also A, B, C. This one also has A, B, C. All of them have A, B, C like that. And then you interpret the vertices as brackets. So this one gets interpreted as the bracket of A and B, that's this vertex, which is fed into another vertex, so it's the bracket of this with C. So each one of these is a bracket of an iterated bracket, and in fact the three of them together make the Jacobi identity. Applying the STU relation is precisely replacing a bracket by, or replacing this bracket symbol by AB minus BC. And the 12 things that you get here, if you read them along the skeleton, so I don't know, let me just give an example. So if I put A, B, and C here, then reading along the skeleton, I read B, and then A, and then C. So each of these becomes a term in the expansion of the Jacobi identity, and since we verified it, the Jacobi identity already, we've also verified this. Okay? But again, it's brainless whether or not you identify it with the Jacobi, with the proof of the Jacobi identity. The second thing is to prove the anti-symmetry relation. So for similar reasons as in the case of IHX, you may as well assume that this is an anti-symmetry relation that sits directly on the skeleton. And then basically, again, it's a brainless verification. Everything cancels. You just reduce the vertex to the skeleton. The only kind of thing is that, so if you have a vertex oriented counterclockwise plus a vertex oriented clockwise, so counterclockwise becomes this difference, and the STU relation was stated drawn in the plane. So the assumption was that this vertex is counterclockwise. If it's clockwise, you first have to write it as a counterclockwise vertex. So the clockwise one you first have to replace with this, and then you apply STU and you get these two pictures, and again this one cancels that one and this one cancels that one. End of story. Okay, questions, comments? Okay, so the next thing is I wanted to tell you again more about how to get weight systems out of Lie algebras. And again, remember what's the point? The point is that functional on A by the fundamental theorem, which we haven't proven but we have motivated. So functionals on A correspond to knot invariants. So really I'm going to tell you that for every Lie algebra in representation, there is a knot invariant. So, okay, reminders. Sorry, I wanted to write, I don't know, let's make it black this time. So, reminders. So, before I name the Lie algebra L, I think I want to go back to Gothic G, which is one of the standard names for a Lie algebra. So suppose G is a metrized Lie algebra, and the Lie algebra we've defined, it's something with a bilinear antisymmetric bracket which satisfies the Jacobi identity. Metrized means that there is a bilinear form from G into G tensor G into the ground field. Again, I'll call it Q, but it really doesn't matter. And which is, what was it? Symmetric symmetric non-degenerate invariant and symmetric non-degenerate and invariant, that's all. And invariant, I wrote last time, means the following. If you look at z bracket x and take the inner product with y and add to it x inner product z bracket y, you get 0, and maybe later I'll go back and motivate this. At the moment, that's just what it is. Okay? But I will comment that all standard Lie algebras, well, all so-called semi-simple Lie algebras, all classical Lie algebras, so all the Lie algebras that you see on books in books on representation theory, so GLN, SLN, SON, SPN, the exceptional ones, E5, E6, E7, E6, E7, E8, G2, F4, all of them are metrized Lie algebra. And in fact, there is more. So there are some metrized Lie algebras that are not among that family, and maybe we'll get to them later. Okay? And the second thing, the second ingredient that I need is a representation. So I need R, which is a representation of G, and let me say it in very few words. So it's a morphism rho going from G into the endomorphisms of some vector space. So the endomorphism of a vector space, and usually the representation is named after the vector space, so the vector space is also called R. So R here is a vector space, and here it's a name for the representation in that vector space. But what it really means is, so the endomorphisms of a vector space are just a copy of GLN. Okay, so they're just matrices. So this is really GLN for some n. In fact, the n is the dimension of the representation. And when I say so this is in itself a Lie algebra using the usual bracket. A bracket B is AB minus BA. And when I say a morphism, I mean a morphism of Lie algebra. So it has to respect the bracket. So this should be a morphism of Lie algebras. And if you want me to write this in more details, that's like saying that we have a map rho from the Lie algebra into n by n matrices for some n, which has the property that rho of a bracket is the bracket in the endomorphisms, or in GLN, which amounts to saying that it's rho of x, rho of y, minus rho of y, rho of x. Okay, what's the point? The point is that this is an abstract group, and this is a realization of it, or abstract algebra, and this is a realization of it within matrices. People care. They happen all over the place. Okay, so I've defined everything, and now I can state a theorem, except it's not really a theorem. You'll see in a moment what I mean by that. So The theorem says that given a finite dimensional Lie algebra, Gothic G, and a finite dimensional representation thereof, so a representation of this Lie algebra, and let me call it R, I claim that there exists something called W of G and R, and it is a weight system. So it is a functional on A with values in the ground field. Okay? Which means in particular, so assuming the fundamental theorem, which again we haven't yet proven, this means that, so a functional on A is a functional on AM for each M. Okay? So this means that a finite type, not invariant of knots, but not just one, for each number M. So lots and lots of them. For each pair Lie algebra and representation, infinitely many invariants, and there are many Lie algebras and many representations. Okay? So why is this not a theorem? Because you know, a theorem cannot say that an object, well, a theorem cannot say that an object exists without saying without giving properties of the objects, right? Of course there exists such a functional. I could just declare it to be 0. Okay? So this is not really a theorem, it's more like a theorem combined with a construction. So it's a construction slash theorem, which really means it's a construction that I'm about to give, and then a little theorem that says that the construction works, that the construction delivers. Okay? So I really just have to tell you the construction, first of all. Okay? So here is the construction. So the first bit is to convert the Lie algebra into lots and lots and lots and lots of numbers. Okay? And then assemble these numbers in the right way. So first of all, we choose a basis. So G is a basis for the Lie algebra. So G is in a vector space. So in particular, it's a vector space, so it has a basis. So let's call the basis x sub a, where a runs from 1 to the dimension of the Lie algebra, which I assumed was finite. Did I also say that the representation is finite dimensional, or did I forget this? Yeah, for every finite dimensional representation. Right. Similarly, I want a basis for the representation. So let me call the vector space of the representation will be the vector space spanned by vectors E alpha, where alpha runs from 1 to the dimension of the representation. Now once I have bases, all transformations, bilinear maps, metrics, whatever, can be expressed in terms of the bases and become lists of numbers. So let me give those numbers a names. So first of all, if I compute the bracket of two basis elements, xa and xb, then I should be able to write it as a linear combination of basis elements. So this should be writable as a sum of the basis element x sub c with coefficients that I will denote f, a, b, c. Okay? So those f, a, b, c are just these coefficients. They're elements of the field. They're numbers. Okay? And by convention, so I don't know if you've seen the Einstein summation convention. Summations are often dropped if you have two indices and which one is written up and one is written down. Okay? So I'll simply write it as f, a, b, c, x, c, but there is so automatically when you see an expression like this which has one upper index and one lower index, the two are summed over. Okay? So this is really a summation over C. Now, these numbers that occur here are called the structure constants of the Lie algebra. And they essentially determine the Lie algebra because because with them you know the bracket of basis elements, and if you know the bracket of basis elements, you know the brackets of everything else. Similarly, let me continue. So similarly, there is the metric is determined by how it acts on basis elements. So if you take the inner product of xa with xb, then this is going to be some number which I will call TAB, and it's just called, what is it called? The metric tensor, the metric, I don't know, the metric matrix, okay? And in fact, the assumption that the metric is non-degenerate, well, it basically means that whatever you put here, there is something here that will make the inner product non-zero. And if you think about it, it amounts to saying that this matrix has no kernel. And since it has no kernel, and it's square, it's invertible. So TAB has an inverse. So let me also give a name to the inverse. The name to the inverse of TAB will be TBC. Where what matters here is not that I changed the name of the indices, but that I've moved them from the bottom to the top. So if I write T lowercase ab, it's the metric, and if I write T subscript AB, that's the metric, and if I write T superscript BC, it's the inverse of the metric. What does it mean that this is the inverse? It means that if I multiply the two matrices, well, what is matrix multiplication? You write TAB and TBC and you sum over one of the indices, and by my rules, by the Einstein summation convention, this summation is automatic. So this should be the identity matrix, and the identity matrix is simply the matrix delta AC. This is the Kronecker delta symbol. Are you with me? Okay, good. So now that I have these, I can define the all lower structure constants, so FABC. So you have to be careful because symbols change their meaning if the indices are below or above. So before I had FAB with C above, and now I have F lower ABC. So this symbol is the inner product of x, sorry, not this x, capital uppercase X. So the inner product of XA bracket XB with XC. So I have two things to say about it. First of all, this assuming the metric completely determines the Lie algebra, because if you know the inner product of a bracket with any vector, you also know what the vector was. What the bracket was. So this also determines the Lie algebra, and I can also write it in terms of the old structure constants. Namely, this becomes a sum over C. Sorry, I cannot use C because I already used it. So this becomes a sum over D of F, D, A, B times XD. And then I take the inner product of XD with XC, which just means that I multiply this with TDC. And again, I don't need to write the summation, it's implicit. So this symbol is determined by the previous two. And then the last thing of that nature is I need to do the same to the representation. So what is the representation? So the representation is, well, a basis element of the Lie algebra, so some x sub a, acts on a basis element of the representation space. More fully, I should have written this as the representation of xa acting on E alpha. So this should be a linear combination of E betas. So I need to give a name to the coefficients. The coefficients depend, so I'll call it lowercase r. Maybe I'll make it look a little bit more like r. So this should depend on A and alpha. And it is summed a summation over beta. So it's R A alpha up beta. And okay, so the few sort of tensors that I wrote, this one, its inverse, the structure constants, the all lower structure constants, and the representation symbols determine all the information that I have, that I've put in. And maybe I'll say one more word before assembling this together. Okay, the FAB upsi symbol is antisymmetric because the bracket was antisymmetric. If you flip A and B, then you get a negative sign. So here, if you flip the two indices, you have antisymmetry. The TAB symbol, so the inner product was supposed to be symmetric, so the TAB symbol is symmetric. If you flip these two indices, the answer doesn't change. The inverse of a symmetric matrix is a symmetric matrix, so the TBC symbol is also symmetric. And finally, the FABC symbol is clearly antisymmetric in swapping A and B, because swapping A and B becomes the antisymmetry of the F symbol. But it's also of the normal F symbol. But it's also antisymmetric in flipping B and C, and I will not check it, but it is precisely the axioms that the inner product is invariant. If you expand what does it mean for the inner product to be invariant, it becomes this. So in fact, this symbol is so-called totally antisymmetric, which means that if you permute the three indices using any permutation, you get back the same thing multiplied by the sign of the permutation. Okay, good. Now, okay, so now finally I can give you the construction. So suppose I have a trivalent diagram, and let me pick one arbitrarily. So what I'm going to do is going to be, I think my convention before was to make the inner lines green, so I'll do it. So I'll give the construction on an example, but it will be clear that the construction is general. So first of all, I test my ability, my vocabulary, or my understanding of the Greek and Latin alphabets. Okay, so I put a Latin letter on every end of every green line. Okay, so maybe I'll put A here, B here, C here, D here, E here, and I still have those ends near this vertex. So I'm running out of Latin letters, so I'll do A prime here, B prime here, and C prime here, and I'll declare that primed Latin letters are Latin letters. Then I put a Greek letter on every external edge. Okay, so where should I start? I don't know. Alpha, beta, gamma, delta. Oh, good. Epsilon. I'm done exactly as far as I know the Greek alphabet. Okay? And now I will write an expression. So near every internal vertex there are 3 letters. So in our case there is only one internal vertex, so I'll use this rule only once. So these 3 letters become F sub, so the structure constants where everything is lowercase. So F sub A prime, B prime, C prime. Now, around each edge there are 2 letters, so I'll use the inverse metric for these 2 letters. So T A prime, T B prime, B prime, T C prime, and finally T E D. Okay? Then each vertex around the skeleton has one Greek letter before it, one Greek letter after it, and one Latin letter facing it. So I'll use the representation tensor letters for each of these. So I'll keep multiplying, and here I have R, A, beta, gamma, R, B, gamma, delta, sorry, the other way, B, gamma, delta, R, D, delta, epsilon, R, C, epsilon alpha, R, E, alpha beta. And I think I'm done. There are 5 R's and 5 vertices around the skeleton. So I'm done. I'm done. I mean, now there is the Einstein summation convention, which tells you to sum over repeated indices. And if you look at this, every index got repeated. Basically because every edge has two ends, and every edge, well, automatically every index got repeated. If you want me to end, so this is automatically summed over, so this is an element of the ground field. If you insist, just once I could emphasize that this is a summation. So this is a summation over A prime, B prime, C prime, A, B, C, D, E, alpha, beta, gamma, delta, and epsilon. No, and epsilon. Okay. Lots of things to check. First of all, the edges were unoriented. So how did I know whether to write TAA prime or TA prime A? Doesn't matter, T is symmetric. The vertices were oriented. Sorry, the vertices, there was no ordering of the vertices, only a cyclic ordering. So how did I know whether to write A prime, B prime, C prime, or C prime, A prime, B prime? The answer, again, it doesn't matter. So Chinmaya, you're speaking, but your microphone is off, so I cannot hear you.
No, I was just sort of mumbling to myself.
Okay, fine. So basically, this is the anti-symmetry of, the total anti-symmetry of the F symbol, which in particular means that it's symmetric under cyclic permutation. So long as I write Z's in the cyclic ordering dictated by the orientation of the vertex, I mean, there is only, this factor is well defined. Now, the R symbols, there are no issues about them. Okay, so no symmetries are needed. Now the harder thing. Why is this independent of changing bases? So, I mean, the way I wrote it, this is highly dependent on whether you choose, which basis do you choose? Okay? So, a physicist would say that if you change bases, the lower indices are covariant and the upper indices are contravariant, and when you contract covariant and contravariant indices, you get things that are independent of the basis. So people see it all the time in differential geometry, in general relativity, where you have to contract metric tensors. It's the same here. If you don't want to be a physicist, then it becomes a mess, but not a particularly interesting mess. Namely, so suppose you change a basis. So suppose, for example, suppose for example, you have a new basis y, ya, and y is written as, or ya is written using some matrix mab times xb. So here you'll have this matrix, here you'll have this matrix, and here you'll have this matrix. So the F symbol for the y basis will be the F symbol for the x basis with 3 times the matrix multiplying it. So the matrix multiplying it sort of on each index separately. Now, the same will be true for TAB with the but with only two copies of the change of basis matrix, and upper TBC will transform using the inverse matrix. And I'm doing it without details, but if you just play with it, it will come out immediately. So basically, here, so if I change basis to everything, then F will get multiplied by 3 m's. Okay? The t with the upper indices will get multiplied by 2 m's, but inverses. Let's call them m bar. This t will be multiplied by m bar. This t will be multiplied by m bar. This t will be multiplied by m bar, sorry, both of them are inverses. And finally, all of these tensors will change, will correspondingly change, so they will be multiplied by m for the change of basis of the Lie algebra, but then there will also be a similar change of basis for the representation, so you'll have n bar, and so on. So if you rewrite this in the new basis, you'll get the same expression, but with extras, lots and lots and lots and lots of m's and m bars and n bars. Okay? But the m's correspond to the lower indices, and the m bars correspond to the upper indices, and the n and the n bars are the same but for the Greek letters. But since this was a contraction, so basically we summed over repeated indices, and the repeated indices are always one below and one above, you'll find that you end up multiplying an M matrix with an M bar matrix, and they cancel. And then this M matrix with this M bar matrix, and again they cancel. So basically all the change of basis matrices will cancel, and the result will be independent of the choice of basis. So I did it in 5 minutes. I could do it in 30 minutes. You will not be any wiser. Okay, it will be, okay? There is a more abstract way to do it. So maybe I'll say it in one word. I mean, how are people familiar with tensor product of spaces? Oh, they are, because we talked about it, okay? But really, each of these tensors can be interpreted as lying in some tensor product of spaces. So f with 3 lower indices really lies in G dual tensor G dual tensor G dual. T with 2 upper indices really lies in G tensor G. And the representation tensor really lies in G dual tensor R dual tensor R. Okay? And the operation written here can be interpreted as tensor contraction. So if you have a big tensor product of spaces, and in it there is a vector space and its dual, you can evaluate the vector space, the dual element on the vector space, and then you get a tensor product of fewer vector spaces. So this can all be interpreted as tensor contractions, and mathematicians know that they are basis independent. So I could have done everything without using a basis at all. Okay? Well, but I'm not done yet. I still have to prove the antisymmetry, the STU relation, and the IHX relation. So far, I mean, until now, we have a functional on diagrams, and it's a well-defined functional on diagrams. But I also want to show that it satisfies the relations in the space A. Okay? So antisymmetry clearly, so antisymmetry just means reversing the order of an internal vertex, and that clearly negates the result because F is totally antisymmetric. So this is really the antisymmetry of the Lie algebra. The IHX relation Let's see what does it mean, or what does it become. Again, I can write everything in extreme detail, but it will not make you wiser. The point is to understand what it becomes. So really, really, if I'm writing IHX, I may as well write it in green, because the IHX is made out of internal edges and vertices. Now, each vertex becomes a copy of the structure constants. The structure constants are just an encapsulation of the bracket. So this really becomes a bracket of brackets, or a bracket of a thing that represents two brackets. This is another thing that represents two brackets, this is another thing that represents two brackets, and I claim that their sum with appropriate signs is equal to 0. But that's exactly the Jacobi identity. So this is the Jacobi identity. We've already seen it, but it's also the Jacobi identity in this context. And finally, the STU relation, so let me write it in full. So the STU relation is really a relation of this form. Okay, and if you read this very carefully, then the left-hand side means you take the bracket in the Lie algebra and then you represent it as a matrix. So the left-hand side becomes rho of the bracket of two things. This becomes, you represent one thing as a bracket, you represent one thing in the Lie algebra, you represent the other thing in the Lie algebra, and then you multiply them in the representation. Right? There is some summation on the index in the middle here, and this summation becomes matrix multiplication. So this is really rho of x, rho of y, and this is rho of y, rho of x. So this is the defining property of representations. I like to call this property representations represent. That's what the property says. Okay? And that's the end, QED. So, I mean, it's not... Okay. Is it ugly or is it pretty? So, the details are immensely ugly. Okay? But the overall thing is basically rather simple-minded. Basically, algebraic data becomes tensors, okay? And these tensors can be assembled in all sorts of ways, and it turns out that these ways are precisely enumerated by diagrams, okay? And the identities between the tensors become equations between the diagrams, and it's pretty easy to read which equation is what identity. That's it. I wish I had time to continue and tell you about GLN, but I'll tell you, so you know we're out of time, so I'll only tell you what the next topic will be. So the next topic will be, I will compute all of these things precisely for GLN. So for GLN, I will compute FABC, I will compute TAB, I will compute RA alpha beta, using the defining representations, and all of these will become just delta symbols. But the point is that those delta symbols will be assembled together in a very neat way as dictated by the diagram. And, well, we'll see what it gets. Okay. See you on Friday. Okay?
I had two questions.
Oh, sure.
So first of all, I mean, since we're going straight to computation, that's what I'd ask.
Sorry, since we what?
This construction, so I said since we're going straight to computation, next time I thought I'd ask you.
Yeah.
This construction should have some properties that we care about, right? I mean, the theorem did not state any properties, but there must be something.
No. The construction has properties that I cared about, and I already stated them. The construction has the property that it is that it respects the relations of calligraphic A.
Right.
Namely,
That's just so we get an invariant. Okay, so I guess that itself is interesting enough to care about it.
That is so for every Lie algebra and representation we get a not invariant, and later I will say that for SL2 and the two-dimensional representation you get the Jones polynomial. For I'll start saying for different Lie algebras you get different known not invariants. Okay?
Also, is there sorry.
Yeah.
Yeah, is there a more, so currently we saw sort of an algebraic combinatorial way of thinking about it. Is there a more geometric way of thinking about it in terms of, you have a Lie group and a left invariant metric on it, and let's say the Lie group has a representation, and there's some interpretation in terms of the manifold you get out of doing something to the nodes represented in the diagram or something like that?
The answer is no. So this is the way to think about it. I mean, maybe you can replace tensors in a basis, the way I wrote it, with abstract tensors in tensor product of vector spaces, but that's sort of a minor, but at the end of the day, we're talking about, but at the end of the day, it is what it is, that's it. Now, okay, this kind of things is actually more general. So I wrote, I used Lie algebras and representations, right? But there are similar calculi for different types of algebras. So, there's something called Poisson algebras. So there are other types of algebras for which you can do the exact same treatment, and then instead of the space A that we got, you will get other spaces of diagrams modulo relations. And they may or may not, sometimes they are, sometimes they're not related to topology. Okay? But yeah, sorry, I actually didn't answer your question. I just added a comment of my own. Okay, any other thing, or can I turn off the video? Okay, so the video